Good morning, sir. I am Kavya Levity of Section A to CSE branch, and my topic for TA is Deutsch Algorithm. A quick introduction of implementation of Deutsch algorithm is that in quantum computing, it was the earliest algorithms demonstrating the power of quantum computing over classical methods. It solves a specific problem determining whether a given function fx, which maps a single bit 0 or 1, is constant, that is, same output for all the inputs, or balanced function, that is, 0 for one input and 1 for one input. A brief introduction and history of Deutsch algorithm is that the Deutsch-Josa algorithm is a deterministic quantum algorithm proposed by David Deutsch and Richard Josa in 1992, with improvements by Richard Clive, Arthur Eckert, Chiara Machiavello, and Mikhail Mosca in 1998. It is one of the first examples of a quantum algorithm that is exponentially faster than any possible deterministic classical algorithm. So the classical solution for solving this function was that for a conventional deterministic algorithm where n is the number of bits, the equation given in the PPT, evaluations of f will be required in the worst case to prove that f is constant. Just over half the set of inputs must be evaluated and their outputs found to be identical. For a conventional randomized algorithm, a constant number of evaluations of the function suffices to produce the correct answer with a high probability. However, evaluations are still required if we want an answer that has no possibility of error. Given the quantum solution of this state, the Deutsch-Josa quantum algorithm produces an answer that is always correct with a single evaluation of f. The algorithm begins with the bit state given in the PPT. A hardware gate is applied to each bit to obtain the following state. Now, the following slide shows the equation and the circuit diagram about the quantum Deutsch algorithm. Here we can conclude that the probability for a state k to be measured is 1 divided by 2 to the power n summation of minus 1 to the power fx into minus 1 to the power x minus k whole square. The probability for measuring k is equals to 0 corresponding to kth 0 is 1 by 2 to the power n summation of minus 1 to the power fx the whole square. Now implementing Deutsch algorithm, we are given a quantum implementation of the function f that maps kth x and kth y to the XOR function. Kth x input is given to be as 0 and kth y function input is given to be as 1. Applying the function XOR to your current state, we obtain the following equation. Implementing Deutsch algorithm to the given function, here we get the truth table of the function given to be as an XOR gate. The truth table XOR function is given as if both the inputs are same, the output will be 0. If one of the input is 1, then the output would be 1. Here is the given equation. If f of 0 is equals to f of 1, the function is constant, and if f of 0 equal not to f of 1, the function is balanced. If applying the Hadamard gate to this superposition state, we get the same function as demonstrated below. If f of 0 is equals to f of 1, the function is constant. If f of 0 not equal to f of 1, the function is balanced. Here we conclude that classically this requires evaluating twice, but using Deutsch algorithm we can achieve this using one evaluation, proving Deutsch algorithm is more efficient and more likely to be used in future. If we talk about the implementation of this algorithm in the modern computers, we can use the Qiskit quantum computing. IBM Quantum provides Qiskit, an open source software development kit designed for quantum computing. Qiskit enables users to build, optimize, and execute quantum programs on quantum hardware or simulators. The quantum circuit shown here is from a simple example of how the Deutsch-Josa algorithm can be implemented in Python using Qiskit, an open source quantum computing software development by IBM. Thank you so much.